Hello everyone, welcome back to my tutorial. In this tutorial, we are going to solve this pressure vessel problem using salome. So I have a pressure vessel of inside diameter of 2 meter and outside diameter of 2.1 meter. It has a length of 5 meter. So to solve this pressure vessel using a cell element, so we can take a top surface or bottom surface. It's better to use mid surface. So I have just taken a mid surface of a radius 1.025. Okay. So here I just converted from that we have a thickness of 0.05. So we have to take the mid surface, that's it. So from the mid surface we have to take it. So I have taken a material of just steel with an X modulus of 210 gigapascal and Poisson ratio is 0.3. These two material property is enough to solve this linear static analysis. So density is just an extra property. Then this pressure having inside the pressure of 1 e power 5 pascal. Okay. So to calculate the hand calculation, hoop stress we are getting around 2 e power 6 Newton per meter square. That means 2 megapascal. Longitudinal stress is half of the hoop stress, which is 1 e power 6. Now we'll solve this problem using salome by using a shell element. There are different shell element which is available in code Aster. So here you can see in code Aster there are different shell elements are there. Yes, this one is the document. So note of use of elements, plates, hulls, grids and membranes. We scroll down here. DKT is nothing but Dirichlet-Kirchhoff triangle element. So triad 3 we can use. Triad quad element we can use for linear geometric. So DKTG also we can use it for the same. Linear or not linear geometrical we can use. DST, this one. And here there is an option called for elements of curved hulls resulting from models 3D with the kinematics of hull are gathered under modeling following. Two is there. One is CoQ 3D and CoQ axis. CoQ 3Ds we can go for biquadratic elements. Tria with 7 node and quad with 9 node. Structural 3D with an unspecified geometry into a linear geometrical, non-linear geometrical and the following pressures. So these elements we can use it. This is a solid element. This one is the plate and this one is the CoQ element. CoQ means shell. Now I have taken, so in this case I am going to use CoQ 3D element. So we will solve this using salome. First we have to model this geometry. So first just go to basic and circle. OX radius we have to specify it. So the radius is 1.025. Just put the radius here. Just apply. Fit screen. Just close. Now we have created the circle. Now by extruding the circle we will get the surface or shell. generation, extrusion, vector is the OX, length it has to be 5 meter. Fit screen, just apply and close. Now we have created the shell. So this both end I am going to fix it. Inside I am going to apply the pressure of 1 e power 5 Pascal. Here you can see 1 e power 5 Pascal. Now I just save this file. Now I have saved it. First we will create the groups to apply the boundary conditions. First group is edge group. I just want to fix this edge. Just press the shift and hold and select this edge. Add it. We'll get both the edges. Here I have to fix it. Fix all. I'm just naming. Just apply. Then surface, we have only one surface. So here I just want to apply pressure. Just apply. There is one more same, we can create the group. This one is the shell. We can keep this pressure itself also, no issues. Now we'll go for a mesh module to create the mesh. Select this extrusion, mesh, create mesh. Here I'm going to create a quad element with only quad. Wire discretization. Local length, I'm just specifying 0.06 or 7 we can specify. Just OK, apply and close. Just right click this one and compute it. Now this is the element I have created. Just see the mesh information. You just go to mesh information. This one is the linear element. We have completely a 2D quadrangle element of 6696 linear element. To solve a CoQ 3D, we have to convert this linear into a biquadratic element. So for just go to modification. There is an option called convert to or from quadratic. Normally it will change it to quadratic, but we wanted in biquadratic element. Just apply and close. Now just go to add modification, add node. Now just zoom and see how the quadratic element looks. This one is the biquadratic element. If it is a quadratic element, this node will not be there, the center node. Biquadratic element having the center node also. So now we have created this mesh. Now we'll create the setup to solve the case. Just go to Aster study. Just say OK. We'll add a setup one by one. Add a stage. Read the mesh first. MAD format. Just apply and OK. And here also you can see every element having two faces. One is positive phase, another one is negative phase. So whatever the pressure where we are applying, that is applied to the positive phase. So inside surface is the positive phase. This dark blue is the negative phase. So orientation also we can check it by using here. In mesh we can check it. So now here we just want to apply the pressure. Now we have read the mesh. Now just go to assign a finite element. Just add it here. Everywhere. Mechanic. Here we have to choose CoQ 3D. CoQ 3D. Just say OK. Just apply and OK. Then this is the shell element. We have to specify the element property. CoQ. We have to choose shell. Say OK. Thickness of this element is 0.05. 0.05. Say OK. Just apply and OK. Now I have created the element property. Then we will create the material. First define the material, then assign the material. So I just naming this into steel. We can keep the same name also, no issues. Linear isotropic material. 210 e power 9 and Poisson ratio is 0.3. Just say OK. Just apply and OK. Now I have created the material property. Then we have to assign the material to the model. Assign the material. Everywhere. We can choose group of element also. Shell. We can choose the shell. Just say OK. Just apply and OK. Now I have assigned the material. Functions and list not required now. Now we just go to boundary conditions load. Assign a mechanical load. Shell element, it has a 6 degree of freedom. It has 3 translation and 3 rotational degree of freedom. To arrest the component, we have to fix all. So 0, 0, 0, 0, 0 and 0. We have to assign to the element group of fix all. Just say OK. Just say OK. Just apply and OK. Now we have created BC. Rename BC. Now just save it. Now we just want to apply the pressure. Here itself we can apply it. Just go here. Press. Just type press. There are different. Press ref is the pressure boundary condition. Assign to the group of element, shell or pressure. Anyone we can choose. Just say OK. This is not required. The pressure value is 1 e power 5. 1 e power 5. Just say OK. Just apply and OK. Now I have created fixed boundary condition as well as the load of inner pressure of 1 e power 5 Pascal. Now we'll create the solver or analysis of static mechanic solver, that is mecha static solver. Here we have to choose this element property also. For solid element only, it doesn't require element property. Beam element, shell element, everything is required element property, because we are simplifying the real-time solid model into the shell. So you have to specify the thickness here. So now just go to loads. So this one is the BC. Remaining thing need not to specify anything. Just say OK, just apply it. Now we have created the solver. Now just go to post processing to create the call champ. Here we have to calculate. For cell element we cannot calculate the nodal values. So we have to calculate the Gaussian element value as well as elemental value. Here also SIEQ Gaussian element, elemental value, Gaussian point and elemental value. Now just say OK. Done. Here it came unnamed. Just use the same name. Just say OK. Then we have to save the result finally. Set output results. So just navigate the file where you want to save it. I just want to save it in the same folder. MED mesh result is, we have to choose call champ, element property. Here tut-75 make it S. Just say OK, just apply and OK. Now it is done. Now see, there is no error here. Now we can solve this case and to view the results. First we just run the case. I'm just giving some more memory. Just 5 seconds I'm making it. Just run it. If any error comes, we have to check it by the message file. Based on the message file, we have to modify the setup. So now we'll open this result file using post processor. So this is showing the displacement value. Now our aim is to check with the hoop stress. So we can directly check with the directional stress, y directional stress. So sigma yy. Just go to sigma elaga or elno. See here, choose sigma xx. Now we just want to check the results of this green color. So just leave these locations. So just select any one of these green locations. So here it is coming around 5.6. Lower maximum all are almost equal. 5.6 e power 5. So the y directional, this is the x direction, that means longitudinal stress we are getting this one. So actually we have to get 1 e power 6. There are huge difference in the longitudinal stress. Now we'll check the y directional stress, that means hoop stress. So hoop stress we are getting almost 2 u per 6, 1.99 u per 6. So here also we are getting 2 u per 6. It's very closer value hoop stress we are getting. So directly we can go for von Mises stress also. So von Mises stress will get same as hoop stress. Here you can see. So almost 1.78 we are getting. So this is the way we can check the results for cell elements. So for cell elements we cannot calculate nodal values, we can calculate only Gaussian values and elemental values. So in this way we can check the stresses. To check the displacements you just go here. So this one is the displacement. Slice also we can check. Y directional slice, none. This is the without deformation. So in this way we can check the values. This one is the magnitude, this one is the dx value, dy, and this one is the dz. So thank you for watching my videos. Please subscribe my channel for more videos. Thank you.